So you have just thrown a ball upwards, not considering air resistance. What force or forces are acting on the ball? Is it the upward force from your hand or the downward force from gravity? The answer is the downward force from gravity, which gradually slows the ball, stops it, then brings it back down, making it fall faster and faster. Without gravity, the ball would just go on traveling the direction of your throw. Without gravity, when you jump, you will just continue on with the direction of your jump into the great beyond. Gravity is what keeps everything in place. It is what keeps your feet on Earth, what keeps the moon around the Earth, and what keeps the Earth around the sun. The concept of gravity was first proposed by Isaac Newton in the 1680s in his book Principia, which contained the universal law of gravitation. As the story goes, he was sitting under an apple tree when the apple fell on his head and he began wondering what pulled it toward the ground. So what exactly is gravity? It is a force that exists between any two masses, two bodies, or even two particles. No matter how small an object is, it still produces a force of attraction no matter how negligible. For example, me and this pen. We both exert gravity, yet our mass is so small that the gravity we produce is not observable. The free fall and the law of falling bodies were first proposed by Galileo Galilei through his Leaning Tower of Pisa experiment, where he dropped two spheres of different masses from the Leaning Tower of Pisa and demonstrated how their time of descent was completely independent of their mass. In Newtonian physics, free fall is any motion of a body where gravity is the only force acting upon it. This is when we neglect air resistance as well as surface area. The perfect environment for the equations that I will be showing is in a vacuum, where air resistance is not a factor. This was demonstrated by David Scott when he dropped both a falcon feather and a hammer on the moon.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
The variables that we will be considering for the equations will be acceleration due to gravity, which will be 9.81 meters per second squared, which is the constant on Earth, initial velocity, final velocity, distance, and time. When solving for free fall, we are given three simple equations. When finding the distance, the formula is initial velocity times time plus acceleration due to gravity times time raised to 2 and all of that over 2. There are two ways in finding the final velocity, and it depends whether the time or distance is given. When the distance is given, the equation is final velocity is equal to initial velocity raised to 2 plus 2 times acceleration due to gravity times the distance. However, when the time is given, the equation is final velocity is equal to initial velocity plus acceleration times time. Gravity is something incredibly commonplace. We're always dropping things. We're not flying off the surface of the Earth. It's a part of our lives from the moment we were born, but it turns out gravity is a really mysterious force that plays an incredibly big part not only in our lives, but also in the universe around us. It is the glue that holds everything together on Earth, in our solar system, in the Milky Way, and the entire observable universe.